Okay, today, ya shabab, we are gonna finish chapter number 12, as I said earlier, and we will start with this problem. This is hopefully gonna consolidate everything we talked about regarding boundary lubrication. So be careful. We are talking about boundary lubrication problem. So here in this problem, let me just try to go over it with you. We have an oily SP 500 alloy brass bushing with a length of 1 inch, a diameter for the bore which is equal to 1 inch also, which operate in a clean environment. This is a very interesting keyword. Why? Because if you recall, F2 depends on the environment and the temperature. And we said if there is no foreign material getting in, then F2 will likely to be 1. So this is a keyword. So at operating at temperature of 70 degrees Fahrenheit, the allowable wear without loss of function, which means W allowable, is equal to 0.005 inch. And then we have a radial load of 700-pound force. The peripheral velocity is equal to 33 feet per minute. And we want to estimate how much is the number of revolution for the radial wear to reach to the allowable value. How much? So we have been given tables from the manufacturer. Let me show them to you in here. So these tables list the specification of this material. It says characteristic pressure in PSI is less than 3,560 psi. The velocity maximum is less than 100 feet per minute. The product BV is 46,700, and the temperature less than 300. These information will become important in the discussion soon. So what do we do? If we go to table 1218, sorry, 12.8, if we go to table 12.8, okay, that table, let me pull it, ya shabab, give me 1 second. Let me pull it here in my slide, so I don't give you some wrong info. I don't want to confuse you. So that table, what does it have? It has the bushing material. So we go for oilies 500, and then it gives us K, which is the wear factor, as well as the BV limit, this maximum limit of pressure multiplied by velocity, which is, by the way, in this table, it is the same as the one in this table, which is this. Look at it. This is the product, 46,700. So if we go there and get the K, so we got the K. Remember, this is K. Its unit is a little bit, lengthy. It is zero point 0.6 multiplied by 10 to the power minus 6 inch cube minute per pound force feet hours. Okay? And the next step is to go and find not the friction, sorry. F1 and F2 are not the friction coefficient. They are coefficient for one of them is for the environment and temperature, as we said. The other one is for the motion, the load, and so on. So if you go to table, let me see, table 1210, okay, what would you see? You would see that, so table 1210, you will see that we can have the motion type, and it makes sense because we just said F1 related to the motion. So in here we have a journal which is rotating, so it is rotary. So we go for the first column. This is rotary motion. Now, the next step is to go for the characteristic length. Now, sorry, characteristic pressure. So let's just look uh, uh, at the pressure يا شباب. If you go and calculate the nominal pressure, and by nominal pressure we said that for a cylindrical journal, the nominal area is this rectangle which will have a length of L and a width of D. So if you multiply D by L, you will get the area. And if you divide the force, which is 700, by that area, and now the area here is this, ya shabab. The multiplication of the diameter and the length, which is equal to 1 and 1, so it is 1 square. And if you divide 700 by 1, you get 700 psi. This is the pressure. So we are actually in the category where we have the pressure, okay, less than 720 psi. So if it is less than 720 psi, we have list of three options depending on the velocity. So the velocity here is 33 feet per minute. So if you go and see the range between 33 and 100, okay, or 3.3 and 33, but be careful here, you need to take the upper limit, here to take the lower limit. Why? Because if you look at table 1210, it will show you that for 3.3 to 33 velocity feet per minute, the coefficient of friction is 1. Sorry, I always say coefficient of friction. The motion related factor, F1, is 1, and it is for 33, it is 1.3. If you go from 33 to 100, what would you expect? Just, continuity. This is going to be 1.3. This is going to be 1.8. So in the end, it doesn't matter. Should you use this limit or that? You should always pick 1.3. Is that clear? So that's why we picked 1.3. Period. Now, for F2, which is the environmental factor, we said there is no foreign material. This is a clean operation, and that's why it is equals to 1. Good, ya shabab. So let's go back here. This is now start getting busy. Now, if you recall also, when we discussed the pressure distribution, we said that in reality, this pressure is not as simple as a uniform pressure, rectangular, same value. No, there is a point where this pressure reaches a maximum value and the distribution is actually kind of polar. And we said that you can integrate what happened. We got the maximum pressure as 4 over pi. Now 4 over pi is telling you that it is multiplied by FDL, which is the same as this. So it is the nominal pressure, but it is multiplied by a factor. This factor, 4 divided by 3.14. So what happened? You have it greater than 1. So it amplified, which makes sense, right? The maximum value is definitely up more than the average. So you get this as 891 psi. Now you go to the table right there, the limiting values over here. Okay, what do you see? You see the characteristic pressure, the maximum characteristic pressure, the velocity, and the BV product. So here, this is why this is less than the maximum value, and that's why we are okay. The velocity is 33 and the maximum is 100. We are okay. And the product 700 by 33 will give you 23,100 psi feet minute, and this is less than the maximum, which is also okay. So you know why these okays are there. Good. Now, what the question is asking about is to find um, how much is the number of cycles. How much? So the number of cycles is calculated as follows. So let me clean this. I don't think we will need it anymore. And just to have this, it's got really busy here. So um, so what happened? The Weir equation. The Weir equation. Add if you forgot it, you should just go back to the notes. Few slide back. This is the equation which we can use to calculate the Weir. So, but here we know how much is this guy. It's supposed to be 0.005. So what are we going to do? We're going to solve for the time. So if we solve for the time, let me go there. This is the equation now. If we solve for the time, look, this is by the diameter. If you remember, we said equals to 1. The length is also equals to 1. And then the wear is equals to 0.005. These are all given. Then we have the 4 as a factor. This is 1.3. You remember the discussion about 1.3? And then F2 is equals to 1. Then what was K? K was zero point 0.6 multiplied by 10 to the power minus 6. And then we have the velocity, which is 33 multiplied by the force, which is 700. Good. So how much is this? Well, if you recall, if we put a consistent unit for in US customary unit, we should get the time in hours. And this is what we got. We got 2,180 hours, which is an equivalent of 1,030,000 and 77 uh, 1,307,070 minutes. Okay. Now, so the rotational speed, as we know, which is, if you remember, we said V is equal to pi d n over 12. So if you solve for n, okay, you will have 12 multiplied by the velocity divided by pi multiplied by d. And this is how much? 126 revolution per minute. So if you multiply this by the time, you will cancel this one is per minute, and then you multiply the time in minute, they cancel out, and you end up with the revolutions. And this is the revolution. It was 16.5 million revolution. To be honest, I don't know in the industry which one is more convenient for them. I would imagine it's always operating hour. They know when did they switch that turbine and for how long it's been running, and then they say, oops, we reach 2180 hours, turn it off. After that we'll have problems, so let's take it to the machine shop and they will fix it. You understand that? Okay. Now the next part, which is the last part in the lecture in this chapter, is the temperature rise. So you would probably ask a question, what, we just spend a lot of time talking about temperature, didn't we? Natural lubrication, pressure vet. So why are we talking about it right here? Well, make no mistake, the 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 whole temperature thing that we discussed during the past lecture was only focused on the uh, hydrodynamic lubrication. And here, where thick film is existing, here we are talking about boundary lubricated bearing, where the film is too thin, and as you see, there is wear and friction and so on. So how are we going to do it? Well, it is not too much different. Actually, we're going to have a few little equations. So we will have the heat generated equation given as this. Okay, so it is 5 by the friction coefficient multiplied by the force, the diameter multiplied by n divided by j. N is in RPM, revolution per minute, and J is a conversion factor, which is 778 feet pound force per BTU. Now, the rate at which this heat is dissipated to the surrounding can be, used using this equation. This equation is what we used before, right? It relates the heat, dissipation coefficient HCR, which we said it is like a compacted coefficient. It has both radiation and convection inside it, and then multiply by the area divided by 2, multiply by the temperature difference. So if we equate the heat loss and heat generation, we will be able to find an equation which tells us what is the temperature of the film, this thin film, which, as you see, is given right here. So if we have a special case for a bearing housing, which is known as a billow block. So this is one type of housing, a billow block. The area, which is right here, look at it, can be calculated easily using this. So this billow block bearing surface area is not complex, and it can be calculated from the diameter of the journal, the length of it, of the bearing, multiplied by 2 pi divided by 144. So what you can do, you can just plug it in here, and you will see that you have a diameter here, a diameter here. So this is going to be simplified to this equation. That, be careful, special for a billow block housing. Okay? If not, then either the area will be given to you, or you might end up solving the problem with a rate type, per unit area. Yeah, whenever you know the area, you multiply it and you get the, the temperature.
Doctor,
Yes,
D and L is in the inch, right?
yes.
Okay.
Okay. So let's look at this problem. This problem is interesting design problem, okay, and I hope you will like it. So what do we have here? We have the same material, this 500 bushing oilies, okay, and we have been told that the maximum wear of 0.001 is desired for for what, a time which is equal to 800 hours with an RPM of 300 revolution per minute and a radial load of 50-pound force. Okay, so what happened here? The problem, if you recall, like the HCR, we have three values: one for still air, where the air is not moving, or we have it for stirred shaft, and we have it for an air with a speed. So here it is actually the middle choice. If you go back to the slide, I think you remember the 2.7 BTU per hour feet square degrees Fahrenheit. So this is for a stirred shaft. Okay, so HCR is given to us, which is 2.7, and we have the maximum temperature, which is 300 degrees Fahrenheit. The friction Fs is given to us as zero point 0.3, and we have been asked to consider a design factor of 2. Okay, so what do we want to do here? We have a manufacturer table, which is given here as, the bushing ID, the bushing OD, and then we have a long list of bushing lengths. But be careful, these lengths, or this combination of diameter or inside and outside as well as length are not available. There are parts that are not available. Only these dots indicate that, oh, you want that, it's available. So this is something to understand. Now let me clean this. I'm going to come back to it. So what do we do here is this. We go and say, well, we seems to have um, some good information about this. Let me show you. So if you go back to the equation, okay, which says that the temperature F is equal to T infinity, which is the surrounding temperature, and it says there is something here, ya shabab. I think in the question it should mention that this is a Below block bearing, because in the solution they have used that area. So let's assume that this is a missing information, and this the housing for this bearing is a Below block. A Below block means we are gonna use this equation. This is what I am gonna write right now. So that area over here is coming from this equation. Okay, I think this is supposed to be written and it is missing. So T infinity plus 720 multiplied by Fs multiplied by F multiplied by N divided by J HCR multiplied by L. So if you look carefully over here, we know N, it's a 300. We know F, and I need to speak about F for a bit. If you recall from 307 and mechanics of material, when you are given a design factor like this, N equals 2 or ND equals to 2, you have two choices. The first choice is to trick the equation and let it think that your material is weaker. So you go to the yield strength and you divide it by 2. Dividing the yield strength by 2 means it's like you are using a different material, but you are not. You are tricking the equation by letting it think that, oh, you're using a weak material while you are using a stronger one. The other way is to take the load and multiply it by n. So you are applying how much? Here, F is 50. No, 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 no. You put 50 by 2, which is 100. You're not applying 100, but that's how you implement a factor of safety. So the design factor here will always be associated. So it makes a lot of sense here to use it on the load. So what are we gonna do? F will become always ND multiplied by F. Always. Okay. So we always multiply the force by the design factor. So if we do that, we know Fs, J is given as a factor for uh, conversion, and HCR is also given here, and L is unknown. But we know what is the final temperature. The temperature for the film, which is 300, a maximum temperature of 300. So what we can and by the way, the ambient temperature is 70. Okay, 70 degrees Fahrenheit. So what do? We can use this equation to solve for L, to solve for L. And by putting these values, we're actually finding the minimal L, the minimum L. It should be this or more. So that's why this equation has been written here as this. L should be greater than or equal to this value. So what happened is when we plug these values, we ended up with an L equals to 1.34 inches. Now the question is, what is the smallest available bushing has that can be used here with an L equal to what? At least 1.34. So if you look here, we have 1.25 and we have 1.5. So it seems that we are stuck with 1.5. We can't go less. So what are we going to do? You look here, there is nothing and there is nothing. So I can't use this option. But if I use this one, 5 over 8 as an ID and 7 8 as an OD, whoa, I have a bearing. I have a bushing here available from the manufacturer. So I'm happy. Let's say, okay, let's try it. How do I know if my selection is good or bad? Because I'm picking now, is to go and say, all right, what is 5 over 8? 5 over 8 is equal to 0.625. So, and L is 1.5. This is what I picked. I picked, I picked this and this. Why? Because this is my selection. Now, if I divide D over L, which is equal to 0. Sorry, L over D. I'm sorry, Shabab. So if I divide L over D, which is 1.5, divided by 0.625, what would I get? I would get 2.4. Now, how is this going to help me? Last class, we stopped here. There. Yeah? Do you remember? This is the recommendation. So 2.4, 2.4 is bigger than 2, and we don't want to be bigger than 2. So what are we going to do, Yashaba? We pick another one. We pick another one. So we go back to the table and we say, all right, let's move to the next one. The next one is a 3 over 4, 1 inch and an eighth, and then we have a bearing. We have a dot there. It means that we have a bearing. So now, if I if I go and calculate this, ya shabab, what would I get? I will get a diameter which is equal to how much? 0.75, right? 3 over 4 is 0.75. And what is the length? Is still 1.5 over here. So if I go and divide L over D, which is equal to 1.5 divided by 0.75, what would I get? I'll get a 2. That's right on edge. But remember, I have an equal, say equal, less than or equal to 2. So I say, okay, I'm fine. I'm going to pick that. So now, when I picked that, I know the diameter, the outside diameter, which is D. I don't care about the 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 outside diameter, because this is when the bushing, ya shabab, will be like this, right? It will have, and this is the journal, right? What is important for me is this diameter, right? And the one which is out, I don't care about it. So now the problem got converted into this. I know what are the diameter, what is the diameter, what is the length, based on the manufacturer. So let me check if I am fine or not. So if I go now, do the checklist again. For this oil is 500. I go find the maximum pressure. I go find the nominal pressure. I go find the velocity, and then the product of the velocity by the pressure. So let's do it. This is 4 over by for the maximum, but be careful, F become NDF. That's probably going to be a common mistake in any exam. Divided by DL. Okay, what is the diameter? 0.75. What is the length? It is L. خلاص يا شباب, you already picked it. You need to stick with it. And we have a 2 multiplied by 50. This is 113 psi. So this is less than the maximum limit and we are okay. The next one is the nominal pressure. So the nominal pressure, the only change it was F, it now become NDF divided by DL. So again, the diameter, don't forget, is 0.75 and the length is 1.5. And if you calculate this, of course, remember, always remember يا شباب, if you calculate this before, make sure يعني your eyes, you look at them, the nominal has to be less. If you got them the other way, it means you did a mistake. You did a mistake. So then what do? We calculate the velocity. The velocity now equals to by multiplied by the diameter 0.75 by 300 divided by 12. So this is 58.9. Okay, 58.9. And this is again less than 100, which means we are okay. Good. Now, if I multiply B by V, I will get 5,240 psi, which is less than this a huge number, and I am okay as well, so I'm happy. Now, the last thing, the last thing I need to check, ya shabab, is what? Is the weir. Now, after picking this, you remember we said the area, the length, the diameter, all of these are inside the weir equation. And of course, if you choose different one, you have different weir. So the weir in the problem was given to us, the limit W allowable was 0.001. I by now have everything. The only thing though I need to do is the following. If I go to the table where the F1 is listed, I will find that if I go for 33, I use F1 equals to 1.3. If I use 100, I get this as 1.8. This is from the table. But if I have the velocity, which I calculated in here, I don't know what is the value. So what are we going to do? Interpolate. That's no big deal, right? So I interpolate and I got F equals to 1.5. Good. Now, if we got F1, then there it is, 1.5. F2 is equal to 1. I'm checking these now. K was given to us, or we obtained it from the table, 6 multiplied by 10 to the power. What? This is no, this is an error. معليش يا شباب, just give me 1 second. This is, oh yeah, just be careful. This is 6, okay? In the table, it is 0.6 multiply by 10 to the power minus 10. So if you write it 6, you need to multiply by 10 to the power minus 11. There's no mistake. So I just then we have the factor. Don't forget the factor of safety. It's 2. You have to apply it here. Everywhere you use F, you multiply it by 2. And then the F, the force is 50. Then we have the RPM 300. And then the time, you remember the time is 800 hours divided by 3 multiplied by L. What is L? The one we just picked, which is 1.5. So how much did we get? We got the weir to be equals to 0.00048, which is less than 0.001, which means we are okay. So what is the selection? An ID of 3, 4 of an inch, an OD of 1 1/8, and then L a length of 1.5. Okay, Shabab, that's it.